All right, guys, we are moving on to the conservation of momentum in 2 dimensions. So this is going to get a little more tricky. This is going to involve one object hitting another object. And it's usually going to hit 2 objects, and they're going to move in 2 different directions. So let's just work some problems. The best way to understand this is to dive right in. So it says, during a game of billiards, the cue ball with a mass of 0.17 kilograms strikes the initial stationary 8 ball with a mass of 0.16 kilograms with a speed of 2.6 meters per second. After the collision, the cue ball's path is 11 degrees above the original path of the cue ball, and the 8 ball travels 15 degrees below the original path. Determine the final velocity of both billiard balls. All right. So we have our cue ball here, and it says the cue ball strikes the 8 ball. And then we also know our momentum of the cue ball initial. After the collision, we know that the cue ball traveled off in a direction. My pen is running out of ink. The catch is, can I find another black pen? Ha. Of 11 degrees. So this vector right here is the momentum of the cue ball final. Our 8 ball down here traveled off in this downward direction, and it traveled 15 degrees below the original path. This vector is the position of the 8 ball final. All right, so the way we can solve this is through components, and that's going to be the easiest way to solve this. We're going to break this down into components. So momentum is conserved using components, meaning that all of them, meaning that the cue ball didn't stop completely. It transferred some of its momentum to the 8 ball, and we're not traveling in a straight line anymore. This is more realistic because when the cue ball hits the 8 ball, the cue ball still travels, the 8 ball starts to travel, and they travel in different directions. Pool is the best way to visualize this because when you when you start a pool game or when you hit pool balls, you use the cue ball to send them off at different angles. So we can say without a doubt, because of the law of conservation of momentum, that the momentum of the cue ball initial y, because it only has a y component here. There's nothing else, is equal to the momentum of the cue ball final y plus the momentum of the 8 ball final y. The momentum of the cue ball initial y is 0. It's only in the x direction. So I'm going to put 0 here. We're going to break this down and both of these down into components. So when we break it down into components, remember we make our right triangles, and we're looking for y. So we're looking for this on both of them. If you remember, hopefully we have SOHCAHTOA. So the sine of this angle is the opposite over the hypotenuse. So sine 11, momentum, cue ball final, plus sine 15, so opposite hypotenuse, momentum 8, final. So if we want to know the momentum of the cue ball final, we can say momentum cue ball final is equal to momentum 8 final sine of 15 over sine of 11. So I just isolated this momentum cue ball final. All right. So now let's do our x components because we can't go any further than that. So we know the momentum of the cue ball initial x is equal to the momentum of the cue ball final in the x direction plus the momentum of the 8 ball final in the x direction. Again, we're going to use SOHCAHTOA. So we have the momentum of the cue ball initial in the x direction is equal to the momentum of the cue ball final cosine of 11 degrees. So cosine is adjacent over hypotenuse. So adjacent hypotenuse plus the momentum of 8 final cosine 15 degrees. All right, we know from our first problem, we have momentum cosine, or momentum of the cue ball initial x is equal to this momentum of the cue ball final. We know the momentum of the cue ball final is the momentum of the 8 ball final sine of 15 over sine of 11. All of this is times cosine of 11. Plus, we're going to bring this down, momentum 8 final cosine 15. Sorry, that is really not in the subscript there. So I want to simplify, and I have got 2 momentum 8 finals here. So I'm going to say momentum of the cue ball initial x is equal to the momentum of the 8 ball final times the sine of 15 cosine 11 over sine 11 plus the cosine of 15 degrees. At this point, I can solve. So I know that momentum of cosine initial x, the initial momentum was 2.6 meters per second. Equals momentum of the 8 ball final times This comes out to be 2.77614. The momentum of the 8-ball final is going to calculate to be 0.1924 kilograms times meter per second. All right, momentum is mass times velocity. So our velocity of 8 final comes out to be 1.2 meters per second. And I did that by saying momentum is equal to mass velocity. I know my momentum is 0.1924 kilograms per second, and I can calculate my initial mass here, which is going to be 0.16. Because that's the initial velocity, the initial mass of the 8-ball. All right. We need to know the final velocity, though, of the cue ball. So we can go back to number 1. So we can say the momentum of the cue ball final is equal to the momentum of the 8-ball final sine of 15 degrees over sine of 11 degrees. The momentum of the 8-ball final is 0.1924 kilograms times meter per second. So I'm going to get the momentum of the cue ball final is equal to 0.1924 kilograms times meter per second sine of 15 over sine of 11. The momentum of the cue ball final is 0.26096 kilograms times meter per second. I can take the cue ball's weight, 0.17 kilograms. Momentum is mass times velocity. So I'm going to get the velocity of the cue ball final is equal to 1.535 meters per second. I can make my big therefore statement and say, therefore, the final velocities are 1.5 meters per second, 11 degrees above the plane, or 11 degrees above the original path for the cue ball, and 1.2 meters per second, 15 degrees below the original path for the 8-ball. All right. That's a lot of work to solve one problem. So there's another way that you could solve these problems. You can solve this type of problem by forming a triangle using the 3 vectors. So we know that we have the momentum of the cue ball initial. We have the momentum of the cue ball final, and that's 11 degrees we have the momentum of the 8-ball final. That's 15 degrees here. Because of our Triggs laws, I can say that this, or our angle laws, this is 15 degrees as well. This is going to be my theta. I can say that the angle theta is equal to 180 degrees, because all the angles have to add up to 180, minus 11 minus 15. So angle theta is 154 degrees. I can calculate my momentum cue ball initial is equal to its mass. The problem says the cue ball's mass is 0.17 kilograms. And it says its original velocity is 2.6 meters per second. So the momentum of the cue ball initial is equal to 0.442 kilograms times meters per second. And now I can use sine law. The momentum of the cue ball final over the sine of 15 is equal to, we know this momentum cue ball initial, so it's equal to the momentum of the cue ball initial over the sine of 154, or the sine of theta. We're going to plug in what we know. So we have the momentum of the cue ball final is over sine of 15 is equal to 0.442 kilograms times meter per second over the sine of 154. I'm going to multiply this side times the sine of 15. So the momentum of the cue ball final is in a vector. I keep making that mistake. Is 0.26096 kilograms times meter per second. If I know how much the cue ball weighs, and I know what the final momentum is, I can figure out the velocity. So the velocity of the cue ball final, momentum is equal to mass times velocity. The momentum is equal to the mass of the cue ball was 2.6. Oh, nope, that's not its mass. That's its. The mass is 0.17. I'm sorry. Our velocity comes out to be 1.535 meters per second. That matches with the velocity of the cue ball up here initially. And we know that angle is 11 degrees. To figure out the momentum of the 8-ball final, I can say the momentum of 8 final sine 11 is equal to momentum cue ball initial. I'm just going to go ahead and plug that in, 0.442 kilograms times meter per second over the sine of 154. So the momentum of the 8-ball final is 0.1924 kilograms times meter per second. Momentum of 8 final equals the mass times the velocity. The mass of the 8-ball is 0.16. When I solve, the velocity is equal to 1.202 meters per second. We know that velocity is going to be 15 degrees above, or 15 degrees below. So these numbers come out to match these numbers. So it's whichever way you are comfortable in solving these problems, you will always be more correct and more exact if you add components together. I know it's the longer way to go, but it is the more exact way to go.